let's begin. So this is what we got to the other time. We talked a little bit about register addressing in the last class. Those are the three kinds of direct addressing modes: immediate, register, and direct memory. Okay, so the immediate, we mentioned last week that here you are using a specified value, all right? So it's either you are moving a specified value into some register, you know, and so on and so forth, right? And then we have the register addressing, you know, so we've talked about all of that: register addressing, immediate addressing, direct memory addressing. These are types of the direct addressing modes, okay? And then you would get to the indirect memory addressing or addressing modes, where you have also register indirect, register indexed, and then instruction pointer relative. Okay, so these are also the three subtypes under the indirect memory addressing. Okay, and then we also talked about move instruction, which we know that you have a destination and a source, pretty simple. And then we said that these are the kinds of move instructions you can do: register to register, register to immediate, memory to immediate, and so on. But you can see that you cannot do memory to memory, okay? You cannot do a move instruction with memory to memory. So you should take note of that. Okay, so NASM would provide you the opportunity to define directives for reserving storage space for variables. Okay, so you can allocate storage space for an initialized data, or you can allocate it for data that's not been initialized. Okay, so there are two cases for that. So the syntax, you know already: you have variable name, then the defined directive, then the initial value, or maybe even a string. Okay, so maybe you say text, where text is the variable name, and then you say define byte, and then you put the particular string there. Okay, if it is number, you also do the same. I mean, I'm referring to this. So I mean, you can just, if you look at this syntax, you can simply put it in this way. Maybe you say text, txt, then you do db, okay? And then you just, if it is a string, you just put it here. Hi, I, blah, 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 blah. Okay, so this is the meaning of this syntax. That's what it means. Okay, another definition you can give is DW. Okay, DW. And that's what? Define what? Word. And that one you allocate 2 bytes. Okay. And then you can also do DD. This is define double word. Okay, define double word. And then define double word allocates 4 bytes. Okay, so depending on the string you want to pass to the variable, or depending on the input you are receiving, you can create a space, right? You just allocate a space based on what you want. So there is a table for that, which you see right here. So DB, DW, DD, and so on and so forth, okay? And you know, when you use Q, for example, you can use move with Q, okay, as a suffix. So move Q, blah, blah, blah. It means you are dealing with quad word, which allocates 8 bytes of memory for you in that operation, okay? So maybe you will see some assembly code, then it's not your usual move, right? But it has got a suffix like move S, move Q, and so on. All these suffixes have got to do with the particular memory we want to access, the size of the memory we want to access for that particular operation. Now, the second type is allocating storage for uninitialized data here, okay? So where you know that you are now waiting, you are reserving the space for some input. So the directives are RESB, RESW. So reserve byte, you know, you are just reserving how many? 1 byte, right? Reserve word now becomes what? You are reserving a word. And the word is how many bytes? 2 bytes. So that's it. It's very easy. Okay. Now the next thing is this. In a particular program, you can have multiple data definition statements. Then I mentioned that you can use the keyword times. Okay, so times is a keyword, or you can call it like a directive that allows you to do multiple initialization to the same value. So you have seen the EQU before, right? The EQU, we said in the previous classes, is used in NASM to define constant. So there are 2 more that we can talk about in this class, but the truth is that there are even others. Okay, but in this class, we limit our scope to these 3. The first one is the EQU directive, you already know, okay? And then the syntax is here. You just give the constant name, or you can call it a variable if you want, but the constant name. Then you give the EQU and then the expression. So for example, you can have total students EQU 50. What does this one mean? Yes, anybody? Hello? Yes, what does it mean? Yes, you just put a constant value 50 into the total students. All right. So basically, you can in somewhere in the code, you can now refer to total students, right? And then you are actually referring to 50. Now, EQ directive cannot be redefined. Are you guys following? Because they're constant. So you cannot redefine this along in the program. You just use the constant and that's it. Another interesting thing is that you can use the EQU to even work out some mathematics, to work out the area of a square and so on and so forth. Right? You do length EQ 20, width EQ 10, then you do area EQU length times width. So what does this one mean? You are multiplying these 2 constants, right? So 20 times 10 gives you 200. Did we use any assembly register here? Huh? Okay, but if you want to, if you do this and you want to print it in assembly, then you need assembly registers, right? So this is just a code snippet. Now the next directive is the assign directive, the percent assign. Now, the percent assign directive can be used to define numeric constants, just like the EQU. However, this directive allows redefinition. You see that? Whilst the other one does not allow redefinition. Are you guys following? Okay. So, for example, you may define total as what? 10. Okay, so you do percent assign total 10. Now you see how the syntax for this is if you compare to the constant, the EQU, right? Okay. Then later in the code, you can redefine it as percent assign total 20. So you can redefine it. Then now once you redefine it, means that it's going to use this new value, which is 20. Now, the next one we are considering, which is not the last one in terms of assembly, you can read more about it, is the define directive. So the define directive also allows you to define both numeric and string constants. Now, this is similar to using define in C programming. Okay, so for example, you may define a constant PTR as this. You say percent define PTR, and then the value you're putting in there is EBP plus 4. So what it means is that you are replacing PTR with EBP plus 4. Okay. Now, this directive also allows redefinition, and it is case sensitive. Okay. So unlike what we've been seeing previously, where you always need two operands, in this instruction, you only need one operand. So you can do increment, that's INC, then destination. Okay, that's it. So that's an example is here. You can just do increment EDX, then that means that you want to increase this 32-bit register by 1. The decrement instruction is just the same, like you do DEC, then you do it for either a register or a particular value in memory. Okay. Now we go to add and subtraction. You can do a register to register, or you do memory to register, and so on and so forth, but you cannot do, again, memory to what? Memory. You cannot do that. Okay. So what an add and sub operation does is that it clears the overflow and carry flags. What does it mean that it clears? What does it mean? Yes. It clears. The opposite is sets. The opposite for that is sets. If we say it sets the carry flag, it means what? It just turns it on, right? Okay. And it clears, it means it what? So take you through this. Like the gentleman who asked how to access these things. Here we are using a constant called sysexit. Okay, so sysexit takes, this is sysexit and it's taking 1, the value 1. Sysread is taking the value 3. Please remember that. Syswrite is taking the value 4. And then standard input, standard output is taking 0 and 1 respectively. Now, this is going to be a constant definition, actually. And after that, we move to define these ones here. So for example, message 1 is going to be the variable, and then we define the byte. It should be what? Enter digit. This is what we are going to show to the user. So in this program, the user is supposed to enter 2 numbers, and then the program gives the result. Okay. So that's it. So these 2 lines here allows you to define the string that will be passed on the screen for the user to enter the value. And then len1 here is taking the length of this particular value that will be entered. Now, the next step is you want to enter the second digit in the same approach. And then the third digit is to display the answer. The sum is blah, 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 the same approach. And then in the next line, the message or the input for the second number. Okay, so here is a sysread for this for the second number. Read the second number into memory. Okay. Now the third one, or the last one here, is to print the results of the 2 numbers. This is outputting the statement, okay, that is appended to the sum itself. So this is like a print statement, if you would say. Okay. Now we need to do the computation. Now everything has been read into memory. So we need to now work with what has been read into memory, okay? So the first one is you need to create, what is this one? What is this? A pointer, okay? Now this pointer will be pointing to the first number that will be entered. Are you guys following? So move EX number 1. Why do we use EX? Why do we use EX register here, guys? Anybody? Anybody with an idea? What is EX register? It's what? It's a data register, right? And it's an accumulator. Huh? So use EX. So in 64-bit is going to be what? REX, right? Okay, so just that. Okay. So another thing that you may not know is that when you have the number that is entered into the system, you need to convert it into decimal, okay, before the computation can be done. Why are we saying this? The number that you enter will be in the assembly state, it will be perceived as ASCII, okay? So you need to convert from ASCII into decimal before you can actually do decimal computation. All right. And the way to do it is if you do sub EX0, okay, when you subtract 0 from some number, what happens? Is that the same number? Is that also? So no change, right? But this line will only convert it to decimal. All right, do you guys understand? And it's standard. You don't change this. It's just like that all the time. Okay. And then who can tell me if you then want to convert from decimal to ASCII so that it's in the state of assembly to print out, how do you do it? You add, right? Yeah, so that's it. It's just to add. What are you adding? You are adding EAX and what? EBX. It's very simple. Okay. Now, why are we using this line? Add EX0 to convert back to ASCII. Anybody? Because I've mentioned this over and over in the class. Why are we using add EX0? We just did addition and we are converting the results to ASCII. Why is it with EX register? Anybody? Yes, it's the accumulator, right? And then we said also that in the class, we said that when you are adding in assembly, the destination holds the results. You see that? Okay, so nothing actually changes with respect to the source in the next line. So the source is only carrying the value to be added to the destination and the results is stored in the destination. So you better use an accumulator. Okay, that kind of thing. All right. So then you go on. Now we need to push the EX into the result. This bytes or memory space that we reserved. Do you remember? So when we do RES with the box around it or the square brackets around it, what are we trying to say? It should point to the RES thing, right? Okay, that's it. And then we now do a syswrite to print the sum and append it to the first print statement. Okay, and that's it. You do exit. Okay. So that's it. So when you enter the numbers, then you get your results, just like that. You have MUL. So with multiplications, there are two instructions, MUL and then IMUL, where MUL is for unsigned data, and then IMUL is for signed data. Okay. So both instructions will affect the carry and overflow flag. So let's look at the syntax. With MUL, you only need one operand, okay? You know, with add and sub, you needed how many? Two operands. But here you need only what? One operand. And that operand is the multiplier. In both cases of the MUL or the IMUL, the multiplicand is in the accumulator, depending on the size of the multiplicand. And then always the multiplier, and then the generated results is stored in two registers, depending upon the size of the operands. Okay. So what is an accumulator? I've already talked about this a lot. You know what an accumulator is. Okay, so look at this example. when 2 bytes are multiplied. Now this is a like a 16-bit program. Is that also? Okay. So when the multiplicand is in the AL register and the multiplier is a byte in memory or in another register, the product is in the AX register. Okay. Now this may be quite confusing for you, but when we look at a typical example, you may get what I mean. So what it means is that if you look at this chart, AL is 8 bits. Is that also? Can you see from this chart? And is AL an accumulator or not? AL is an accumulator. It follows up with RAX, right? Okay, so it makes some sense here, huh? To say, okay, so it makes some sense here to say that the multiplicand is in what? Is in AL. Okay. And then the source would also be like an 8-bit register or a particular, or in another memory. Okay. Now, the reason why we are saying this is like, maybe you just want to do a 16-bit computation. In assembly, they are saying, in the 16-bit computation, you should know that 2 8-bits make a 16-bit, right? So one of them, which is an accumulator, stores the multiplicand, and then the multiplier is in the other. Are you guys following? Yeah, so that's the logic. When you are multiplying two one-word values, it's the same thing. So for example, AX, now when you come back here, AX is 16 bits, is that not so? But last time, like I was telling you, usually 2 registers will combine to make 1. So here, if you look at this one, this diagram maybe is pretty small for you, but you see that EAX here is made up of AX and some other register, right? Okay, so that's it. So therefore the AX here is the accumulator, and then the other register is going to be the source for the multiplier. If you look at AX here, AX is made up of AL and some other register, right? Are you guys following? Okay, so AL then becomes the one that holds the multiplicand, all right? So it goes on and on like that. And the same if you want to do for double word, then now you are coming to the 32 bits, right? So RAX is also made up of what? EDX and then EAX. Do you guys follow? Aha, so that kind of thing. And then what? EAX is made up of what? DX and AX. You see? Okay. And the H and AL makes what? H and AL makes what? AX. Okay, so move AL 10, right? What does it mean? 10 is going here, right? Okay, so AL is what? Accumulator, is that also? Okay, and then DL takes 25. So DL is a multiplier. That's the source, is that also? So if we do MUL DL, what it means is that we are actually multiplying 10 times 25. Okay, that's all. And then in the signed case, for example, if you change this hexadecimal, you get -1. If you change this, you get this one. So in IMUL, it's also the same idea. Okay, helps you to multiply 3 with 2. Okay, so you can follow along. It's just the same thing. You see that you are doing now. This is where you need to get a trick. You are doing a 32-bit program, but you see these registers. Are they 32? Aha. Why? Why? Because obviously, if you are doing multiplication like we're doing, it's like a reverse. Okay, if you want to multiply in 32, you obviously need 16-bit registers to help you in the multiplication, where one serves as accumulator and the other one serves as a multiplier, that kind of thing. Multiplication overflow does not occur because double length registers are used to keep the product. However, in the case of division, overflow may occur and the processor will generate an interrupt, okay, if overflow occurs. So look at the syntax here. Also, it uses how many operands? 1, okay? And then the dividend is in an accumulator. So remember dividend, right? What's the dividend? The numerator, right? It's in an accumulator, and then the divisor is the one that is the source. So it carries the same notion like the multiplication. So for example, okay, let's look at this one. The div and the idiv affects all the 6 status flags, okay? You'd see that in the picture I sent you, there are some flags that were up, right? We call them like status flags. Okay. So when you want to divide, when the divisor is just 1 byte, the dividend is assumed to be in the AX register. 1 byte means more like an 8-bit register, right? Okay, so the dividend is assumed to be in the AX register in the 16-bit. You see that whilst the multiplication is like a reverse, the division is what? Is on the ascendancy, right? Okay, so if you are doing 1 byte, now you have to leverage 16 bits. Okay, so like that. So it's going to be 16 bits over 8-bit divisor. Okay, and then we are saying that the dividend is the one that is in the accumulator. Okay. So if you are doing if you are doing 16 bits division, then you need a 32-bit dividend. Are you guys following? Okay, cool. So this is also a sample code I encourage you to try, and then you can try to do other stuff yourself later on. Logical instructions. We are about to finish the course. This is the instruction set for logical instructions. You have AND, OR, XOR, test, and then NOT. Okay? You can use them. It's pretty simple. Their syntax are quite easy. You saw the syntax for XOR. You just have 2 registers, right? XOR this register against this register, and so on and so forth. So with AND, you need 2 operands, all the same, but with the NOT, you just need 1 operand. So the first operand in all the cases could be either in register or in memory. And the second operand could either be register or memory, or a constant, or which is usually referred to as an immediate value. But you still cannot do what? Memory to what? Memory operations. Okay, so this is an example, like how to use OR, AL, BL. So this code is supposed to actually output 7, okay, where it's comparing 2 numbers and then outputs just one of them. So you can, later on, you can have a look at it. It involves the usage of OR. Okay. Procedure. Procedure is just the same as what? Subroutine. And this is the syntax. We've done this before, right? So like you have maybe print name. That's the procedure. You bring your full colon, then you put the procedure body there, and you do return, right? Okay. And then now you call the procedure name, just that. Recursion. Recursion is a procedure that calls itself, all right? So there is nothing strange here. Macros. Macros. Writing a macro in assembly is just an idea of modular programming, okay? It's just the same thing like I told you about initially. You start with percent macro and you give the macro name, and then you end with end macro, but you have the macro body, just a bunch of codes in there. You guys follow? Okay, so it's pretty simple. It's borrowing the same idea of procedure, so if you like subroutine. But this time the difference is that you start with the name and you end with a name, right? Okay. So a macro is invoked by using the macro name, just like you invoke a procedure by calling the name. Okay. So you invoke the macro by using its name with the necessary parameters. When you need to use a sequence of instructions many times in a program, you could simply put them together under a macro, and then you call the macro name. Okay. So this is an example. This is a macro with 2 parameters. So and it implements the sys_write call. So like this, macro write string. So write string is what? Is the macro name. Is that also, guys? Okay. That's the macro name. And then you have these bunch of instructions here. This is an instruction for sys_write. Is that also? Yeah. So if we don't want to be writing sys_write for everything, you see, so sometimes in the code you do a lot of sys_write. Is that also? So you just macro it, and then you use the macro anytime. So you then do end macro. So anytime you call write string, then you are calling a sys_write thing. So you see how it's used here in the program. In the text, in the session.text, you see you have write string, what? Write string message1, right? And then learn1. In other words, the parameters that you are passing to the write string is this message1, which has already been defined, maybe in the section.data, and then the length, which has already been defined. Okay. Why? Because here in the macro, you leave the room for defining the message and then the length. Is that okay? So you don't have to write sys_write, a lot of sys_write. It's in an efficient program, like it's too long. So just do one macro that is a sys_write macro, and then you can pass the parameters to it, which is always the message and then the length. Because that's what changes in every sys_write. Yes or no? Huh? Yeah, the others are what? The same. Is that also? So you can do that. So you just, that's one of the efficiencies of using macros. So once you do %1, %2, it means that this is the first parameter and that one is the second parameter that you should pass to it. That's all. And then you can call it at any time, right? Is that not nice? It's nice, right? So that's why I asked them to use macros to build that thing. Okay, so it's not, that means it's not going to be a long program. If you're writing a calculator that does all of those computations, it's not going to be a long one because you are just going to leverage macros and it becomes nicer and shorter. Okay. So I'm expecting that in your project, you use macros and you understand why you use the macro and you'll be able to explain. Okay, let's move on. File management. And this is the last part of the course, file management. And this is so easy. Like when I show you, say, we've done it already. See, it's just about syscalls, all right? Because if you want to open a file, you know the syscall for opening. Is that also? If you want to write a new file, you know syscall for writing, and so on and so forth. So that is it, guys. That's the end of CSM 254. Okay.